Now we talk about minimal spanning trees. Consider a railroad system connecting 5 cities as being planned. The goal is to build a system using the least amount of money while ensuring that each city can be reached by any other city in the system. Based on the distance and terrain, the following chart gives estimates in the cost and hundreds of thousands of dollars to build a railroad between any 2 cities. So we're taking the spanning trees that we just learned about and now putting weights to them and trying to make it the most efficient spanning tree that's possible. So I'm going to go back and forth between these 2 slides, this one and the next one, but we first need to create a graph that models the cost contained in this table. So here we have the 5 cities, A, B, C, and D. And we're first going to look at city A and how it's connected to all the other cities. And then we look at city B, and it's connected to all the other cities. Now it's already been connected to A, so that's why there's only 3 cities connected to B, because it's already connected to A. And then if we look at C and D and how they're connected, we'll create this graph that has all the weights. You should notice that this graph has several cycles, so we need to create the minimal spanning tree by eliminating those cycles. And the best thing to do is begin with the edges that are most heavily weighted. So if we begin taking off the heaviest weight, that's 12, and then 11, you'll see we've eliminated some cycles there. The next heaviest weight is 10, and that occurs twice. And we still have some cycles, not many, but we can see here that E is already by itself, which is good. So we need to eliminate the cycle that contains B, C, and D. The heaviest weight in that cycle is the 9. And then we need to eliminate the cycle that contains C, A, and D. We have to keep the 7 because that's our only connection to B. So it actually doesn't matter if we take off this 5 or this 5. We'll still get the same answer. So the solution to this spanning tree here is 18, and since each of these weights represents hundreds of thousands of dollars, that's $1,800,000, which is $1,800,000. Just another check. You just want to make sure that all cycles are gone, and once that's the case, you have completed the minimal spanning tree. So create the most efficient network, or the most efficient spanning tree for this graph. If we look at this graph, we should notice that we want to keep the smallest numbers, so let's identify those. We want to keep the 2, the 4, the 4, and the 5s. Every other number we want to get rid of if at all possible. So we'll start with redrawing the vertices, and we'll go back and forth between this picture and the next and create the spanning tree. And if we start creating cycles, then we're going to have to maybe use some different numbers, or maybe eliminate one of these numbers that we've circled. So here are the 5 vertices. We want to start with the smallest number, so that's 2. We'll go with the next smallest number, which is 4, and that occurs twice. And if you look here, that creates a cycle. So we can't have this number 4 because a cycle is created. So we'll go to the next one, The next smallest number is 5, and then another 5. And so because of this right here, we can't use this number 4. We got to take it out of there. And here is the minimal spanning tree for this network. And the solution is 16. 4 plus 5 plus 5 plus 2, 16. So let's try that one more time. We have the second network here, and we want to try to keep all the smallest weights without creating any cycles. So let's look at what the smallest weights are. We have a value of 1, 4, 5, 5, and we might have to use one of those 6s. And again, if cycles are created with these numbers that I've just circled, then we'll have to go into some of the bigger numbers. But let's look at this graph and see what we can keep and what we can get rid of. So we keep the 1, then we keep the 4. This first 5 works because it does not create a cycle, and then this second 5 also works because it does not create a cycle either. Now it looks like it turns out if we were to keep the 6, now these two vertices have too many lines going to them. So we can't keep the 6. And now the solution to this weighted graph is 15. So essentially what we've been doing is Kruskal's algorithm. And Kruskal's algorithm has 4 steps. Step 1, put all the weights in a list from smallest to largest. Step 2, find the smallest weight in the list and include the associated edge and 2 vertices, as long as that does not create a cycle. Step 3, remove this weight from the list. Step 4, repeat steps 2 and 3 until all vertices are connected. So we're going to apply Kruskal's algorithm. We're going to start with the lowest weights. The first weight is 3, and that connects island B to F. So island B to F is a weight of 3. That did not create a cycle, so we keep it. Next weight is 4. That is island B to C. B to C, that does not create a cycle, so we're going to keep that weight. The next one is 5. That creates a bridge from island C to F. Now that is a cycle, so we cannot keep it. So we cannot use this number 5. So let's try these 2 6s. These 2 islands are D to G and E to F. So D to G and E to F. Neither one of those create a cycle, so we are good to go when we keep those 2 paths, those 2 edges. The next shortest is 7. And there's 2 of those. So let's take a look. A to E and B to G. So let's see if they create any cycles. So A to E is 7 and B to G is 7. Now if you look here, there are no cycles and every vertex is connected. That means we have created the minimal spanning tree for this chart by using Kruskal's algorithm. And here's the grid. And the solution for this minimal spanning tree is 33. Now that represents the miles that each bridge covers between the islands. Alright guys, that's minimal spanning trees. Make sure you go back through this video and take good notes so you can use them on a quiz and be prepared for the next test.